All right, hello everyone and welcome. This is going to be probably a long video. I'm going to timestamp this one with a few chapters, but this video is going to cover moles. This video is going to cover molar masses. This video is going to cover stoichiometry. So we have a lot to get through, okay? Um, this video is not going to contain some of the stuff that we'll do with our labs in the later half of this chapter. Really just stoichiometry is the big thing. What to expect, moles, what it is, molar mass, how to calculate it, and also what it is, some introductionary stoichiometry, and then putting everything together. Lastly, in this video, I'm going to give kind of a alternative way, I think, to maybe structure the way that we do stoichiometry. There are two methods of solving these types of problems. There is a shortcut. There's a way to organize this, and I'm going to leave the choice as to what you are most comfortable with up to you. But I do want to give you kind of all the stops, all the ways to solve some of these problems. Without further ado, let's get into this. So we are talking about the mole and what exactly a mole is. So I do want to skip some of the introductionary slides that I had in this. The mole. The mole is a quantity. It tells you how much of something you have. You know, this could be talking about anything. You could have a mole of eggs, a mole of elephants. All that matters is it is a certain amount of something. Just like you would say, I have a dozen eggs, and that means you have 12 eggs. If I say I have a mole of eggs, I have 6.022 times 10 to the 23rd of something. And I'll probably use this number, 6.022 times 10 to the 23rd, with the 3 decimal places. So this is an astonishingly large number. This amount of eggs would be, that would be a lot more eggs, probably more than there has existed. This is known as Avogadro's number, 6.022. I just want to highlight this. Avogadro's number. This fine gentleman right here is Avogadro. It sounds like avocado, which is why you see a lot of avocado memes like this one that I have up here. You're going to see a lot of these. Hello, Mr. Avocado. He did not actually find this value. He just kind of postulated that this number exists, which is why it's named after him. Just like grams measures mass, and it's shortened to G as the unit, moles measures amount of stuff, and its shortened version is MOL. So we would say this is mole. Just like you'd say, if you said, alright, I have 5 grams of something, this tells you, instead of 5G, this is 5 grams. Alright, if you said 5 mole, I have 5 moles. That's just what that means. It means I have 5 amount of stuff. This number. 5 times this number amount of stuff. And you might just see this if you had like a formula sheet or something written as capital A sub A. Or capital N sub A. Alright. The calculator stuff, I really, this is stuff that you guys can go over. You can watch previous videos about this. I do want to give this link for the calculator stuff. I'm not sure how in-depth I'm going to really require this stuff. You will have to use the calculator, but I'd rather focus on the stoichiometry and using actual amounts instead. Alright, so our Dalton is our friend, is our unit of mass. We kind of talked about isotopes and how they have different masses, and that was due to a difference in neutrons. So you could have 2 atoms of the same element, and they have a different mass because they have different amount of neutrons. And we talked about how the atomic mass is the weighted average of every carbon atom that we see, or any other atom. This is based off of the Penny lab that we did way long ago. And I think that was the first or second marking period. Either way, if you go to the periodic table, you're going to see numbers that look like this. So here's carbon, and you're going to see 12.011. This is our atomic mass. We talked about this in context of if you took every carbon atom on Earth and found the average mass of it, it would be 12.011 daltons. And each one of these atoms has its own atomic mass, and the reason they're different is because there's different isotopes and different amounts of isotopes, percentage-wise, basically. Okay, so if we go back, get rid of everything else here to our slideshow. Unit conversions. I had my honors class do this just for fun, um, to be mean. But when we start doing this calculation, okay, if you multiply Daltons times their conversion factor, you will get 1. So basically, our conversion factor is saying that the molar mass is the same as the atomic mass. They're not literally the same, but they are the same numerical value. And what that means is if you have 1 mole of H, of hydrogen, its mass, instead of, go back to our periodic table, or we go back to hydrogen, if we had 1 mole of hydrogen, so we had 6.022 times 10 to the 23rd. If we had this amount of hydrogen atoms, their mass would be 1.008 grams. That's what molar mass means. So our units for this molar mass is going to be in grams per mole. How many grams does this 1 mole of whatever you're talking about, whatever compound, whatever ionic compound, whatever molecule, whatever atom, whatever element, whatever anything, how much it weighs, what its mass is per 6.022 times 10 to the 23rd of that ion, compound, whatever you're measuring. Okay? So our units are going to be in grams per mole. So let's take some examples here. Alright, first, as I said, hydrogen would have a molar mass of 1.008 grams. But if we did some other examples, just let's take molybdenum. If you had 6.022 times 10 to the 23rd atoms of molybdenum, it would weigh 95.95 grams. And this puts things into a kind of a tangible amount. I showed you guys in class what a mole of sodium chloride looks like, and it's it's a handful. It's a hefty amount, but it's something that is tangible. You can weigh something that weighs 53 grams. That's not, or whatever your thing is, 95.95 grams. That's a tangible amount. That's not like a single atom. This does say how small atoms are, and that this huge a number of them is a small, is something that we can barely kind of understand. But it's easier. It's numbers that we can use. It's something that we can very easily put on a scale and see how much we have. And we will be doing that in our lab. We will be measuring out amounts and calculating how many moles, how many atoms that we have of some kind of substance that you're using in the lab. Okay? The other thing for when we're calculating, I'll go on here, when we are calculating molar masses. If we take just oxygen, for example, and I'm going to actually pull up side by side. I want to have like a whiteboard, and I want to have the periodic table. Okay, so if we have this side by side, and we click on oxygen. Here's oxygen. We'll clear this section here. Oxygen has a mass of 15.999. I think I gave you, rounding up, I will probably have you round to 2 decimal places when it comes to this. So if this is 15.999, you can just write that as 16.00. You can round that up to 16.00. So if you had a mole of oxygen, it would be 16.00 grams. And I'm going to introduce it to look like this, just for reasons we'll see later. 16.00 grams per 1 mole. By adding in that division sign, you're saying it's over, it's per. So if I have 1 mole, I have 16 grams. And this is a ratio. Very important. Molar masses are ratios, which means that the inverse is also true. If I say, if I have 16 grams, I have 1 mole, I can also say on the same exact statement, if I have 1 mole of oxygen, I have 16.00 grams. These are the same statement. Because this is a ratio, this is true. 1 mole for 16.00 grams, 16 grams for 1 mole. They're just the same statement, just going back and forth. And we'll see why this is going to be important later. All right, so I will start writing things out like this, but this is really just kind of the unit. Our unit is grams per mole. So you can write it grams, mole to negative first if you really want it to be. Have fun. You might see it just written like this. This is the same thing. This is a division sign. Okay. I really want to reiterate this is how many grams you have per mole. So if we go on to our next slide. Okay. If we go on to our next slide, I had to quick screen was out of the way. I asked for the molar mass of O2. Alright. So let's introduce something. You can have, if you have 1 mole of oxygen, you have 6.022 times 10 to the 23rd atoms of oxygen. Atoms. I'm being very emphasis on atoms. However, if you have 1 mole of O2, that's talking about oxygen molecules. The oxygen molecule that looks like this, that has 2 atoms in it. 6.022 times 10 to the 23rd molecules. I really want to emphasize that difference. Because when you're talking about the molar mass of something, that molar mass is the mass of whatever the thing that you have the mole of, which in this case is the 2 oxygen atoms. So if we were just to have 1 molecule of oxygen, we have 2 atoms of oxygen. We have 16.00. That's 1 atom plus 16.00. And we get 32.00. Now this would be in Daltons, but because we have a mole, we're going to use that unit. Grams per mole. That is our unit. So the molar mass of O2 is 32 grams per mole because there are 2 atoms of oxygen in each molecule. Okay? And to kind of codify what I've just done, if we go on to the next example, I look for the molar mass of acetic acid, C2H4O2. Now the way that you're going to be doing this is every single atom in this molecule has a mass. So here's our molecule. Now if we had 6.022 times 10 to the 23rd molecules, we would have all of these atoms, this entire shebang, we would have 6.022 times 10 to the 23rd of them. That's what a mole means. So how do we actually solve for this question? What is the molar mass? Well, first, we have to count out just what the mass of all of these atoms are. So we have here 1 carbon, and I have carbon's mass up here. So we have 1 carbon, but we have 2 carbons. That's what this 2 tells us. That's what our subscript tells us. So, so we're bringing back that first part from the beginning of the chapter, what that subscript means. Plus 12.01. We'll use 12.01. Sorry, forgot. I will use 2 decimal places. All right, that's our carbon. The other way to write this, just for when it gets a little bit more complicated, is instead of just adding this, adding the same number twice is the same thing as saying 2 times 12.01. Put that in parentheses. We go on to the next element, which is hydrogen. Here's hydrogen. We'll use 1.01 times, how many of them do we have? We have 4. Plus, we go to our last element, which is oxygen. Oxygen is 16 from what I had last time. Plus 16. And we have two of them times 2. So let's put this into a calculator. So I'll use parentheses. 2 times 12.01 plus 1.01 times 4 plus 16.00 times 2, close my parentheses. What do we get? We get 60.06 grams per mole. There's our molar mass. Put this out here. Grams per mole. Okay? There's our molar mass. So if you're looking for kind of an easy way to do this, my advice to you is to really just line this up. So what I mean by that, I'm going to clear my screen here. We have these atoms in here. Line this up, just like when we were doing the balancing, and I told you to set, each element. Do the same thing here. So carbon, how many do we have? What's the molar mass? Okay. Hydrogen, how many do we have? What's the molar mass? Oxygen, how many do we have? What's the molar mass? And then all you're doing is taking this and just adding that all up. So this way, if the math is a little kind of scary, you're at least lining it up, saying what my numbers need to be, how many of the atom do I have, and how much does each of those atoms weigh if you have a mole of them. All right, you do the same thing, you're going to get that number, 60.06 grams per mole. Okay? All right, the last thing that I really want to emphasize here is that mass does not equal moles. Mass is how much matter there is. We can think of it for most of our intents and purposes as how much something weighs. That's where that's the best way to think about it. A mole is how much you have of something. It is a quantity. It is a number. It's not talking about mass. It's not talking about weight. It's just a count. Like if I have a dozen eggs, that example I used in class, doesn't tell me much except that I know how many eggs I have. It is a quantity. A mole is the same thing. I want to be very clear with that. All right. Now, where we're going to start in is doing some of these unit conversions. And oh boy, here is where things can get dicey. So, what I'm going to do here is I'm going to break this down into kind of some steps that I think is the best way to get these answers. Okay? Before I start, I do want to go over just a little bit of the algebra review here. Basically, when you have something on the top and the bottom of some function, when you have the same unit on the denominator and the numerator, or numerator and denominator, they will cancel out. If you have an x up here and an x down here, that is the same variable. They will cancel each other out and you can just delete them. When we see this with units, we see it looks like this. When you have milliliters, which is 1 unit, on the top in the numerator, and milliliters, which is the unit in the denominator, they will cancel each other out and you are just left with the grams here. Alright, this is an idea that we talked about way back in chapter 1. I know it was tough and I want to really work on it now because I think a lot of these problems are, it's going to be unit conversions. You're going to be converting between moles and grams a lot. Alright, so that's a little bit of our just recap. Alright, so here is stoichiometry. And I gave this analogy here to really kind of hammer home how this is a ratio. If you need 2 eggs and you get 4 cookies from 2 eggs, that's a ratio. 2 eggs for 4 cookies. If you have 4 eggs, then you would get 8 cookies. It's a ratio. That depends on how many eggs and how many cookies you get. Okay? And just like the molar masses, These are ratios. They are stagnant. They are true. This is a set amount, but it can go on either side, like a chemical equation. 2 eggs goes into 4 cookies. So we have 2 eggs on top, 4 cookies on the bottom. You can do the reverse because this is a ratio. You can have 4 cookies on top and 2 eggs on bottom. These are equivalent statements right there. These are equivalent statements. By having 2 eggs, you are automatically guaranteed 4 cookies. By having 4 cookies, you're getting 2 eggs. How many you end up with depends on this ratio. And it's the same exact thing for a chemical equation. Right? If we take this balanced equation right here, just like those eggs and cookies, you can do conversions with this. If I start with 4 moles of H2O, how many moles of O2 will be produced? Well, let's look at our ratio. Our ratio is either this 2 here to this 1. So if we have 2 moles of H2O, for every 2 moles of H2O, we will get 1 mole of O2. And the reason for this is because we're talking about amounts. So because there's kind of coefficients, if you really thought about it, if you have every 2 moles of H2O, you're getting 1 of O2. So when we did our structures out here, this is what this formula looks like. And we can see this ratio right here. For every 2 molecules of O2, we get 1 molecule of O2. Sorry, of H2O. Every 2 molecules of H2O, we get 1 molecule of O2. So we could just, that's per 1. If you had a dozen, you'd have the same amount. If you had a mole of it, you'd have the same amount. Because it's just a number. It's a count. It's the same ratio that entire time. You will always have a ratio of 2 water molecules to 1 oxygen molecule. So we can write this ratio like this or like this. These are equivalent statements. Now, we start with 4 moles of H2O. So when we're doing this type of question, I'm going to go to the next page. You always want to line up your units so that you have the same unit on the numerator and the denominator. Now, a key kind of note here is that moles of H2O is different than moles of oxygen. You're comparing 2 different molecules, so the amount that you have is a different unit. Alright, just roll with me on this one if that doesn't make sense. In order to cancel out, it must be moles of the same molecule. So moles of oxygen is not the same as moles of H2O. Moles of H2O will cancel out moles of oxygen. So this is what you did. This is what you did. The same thing that you did in the cookie and the egg problem. Okay? You did a unit conversion, whether you knew it or not. So any of these products or reactants can be thought as a ratio. I'm going to call these stoichiometric ratios. That's really what stoichiometry is comparing how much, different amounts based off of this chemical equation. Alright, I'm not going to look for a hard definition of stoichiometry, but when I talk about the stoichiometric ratio, I'm talking about the ratio that you get from the chemical equation itself. You use the coefficients. The coefficients of the chemical equation is what gives you this ratio. Okay? So this is why we've been balancing, we've been finding these coefficients. This whole chapter flows just like water. Very apt metaphor, I know. And here is why I tell you that moles of different molecules are different units. Okay? And I give you some practice problems. We'll go over these in class. Alright? But the way that you're doing this is straight up just by doing a unit conversion. Okay? And I'll let you pause here. We did this in class, but this is always good practice to do again. So I'll let you pause. All right, did you actually pause, or are you just skipping through this? Okay, so I'm gonna go to the next screen. But what I'm gonna talk about is this values that I gave you right here and right here. You always, that's the first number that you start with. Always start with the given amount. So if I'm talking about 3.3 moles of ethene C2H4, that's what you are talking about. That's the first number that will go in your conversion. And see, look, number one, 3.3 moles of ethene. And you multiply this by this ratio. Notice that I have moles of ethene on the top, and I have moles of ethene on the bottom. All right, you could have an invisible thing here just to kind of show you that. But notice here, the same unit cancels out across. This is actually a theme that I'll hit you at the very end. But this acrossness, this is where this cancels out. All right, your units must be across from each other to cancel out. And here you go. You get this 6.6 moles of CO2. All right. You started with, or you ended up with 0.4 moles of carbon dioxide. So you're just working backwards with the same ratio here. Except now, because we have moles of CO2, we use the ratio in reverse. I flipped this ratio up here. I flipped it. Now the moles of carbon dioxide are on the bottom because now we have the same unit across from each other and they will cancel out. All right, 0.4, and then we divide this by 2. We end up dividing it by 2, gives us 0.2 moles. All right. Lastly, this is where things can, the math is a little bit more complicated, and just goes to show you, you can have these weird ratios. You can have 3 moles of O2 to 2 moles of CO2. All you have to do to solve these types of questions is multiply the top numbers. I'll use a different color. Multiply the top numbers by one another, which I did right there. And you're going to multiply the bottom numbers by one another, which there's an invisible 1 here if you want to be, pedantic. And you get this 2. And then you just divide these two numbers. You simplify this answer, you get 0.6. Okay? We're going to start to see a lot of more complicated kind of questions. So that is, in a nutshell, how you would do these types of stoichiometric equivalences. All right, the full stoichiometry I'm going to get back to because I want to get back to the first PowerPoint where we started to convert between moles and grams. All right, so you will have to do these conversions between moles, from moles to grams. All right, this whole thing is going to be unit conversions. And here is our other one, is how many moles do we have if I give you the grams? Because that's what stoichiometry is. Stoichiometry, all these problems that I'm going to ask you, is I give you grams of something, you convert that into moles, convert that from moles of something to moles of something else, convert that from moles back into grams. This conversion that I just had you do, if I go back here, where are we at? This conversion is moles to moles. We start with moles of something and end with moles of something else. So we have to get these moles by converting grams into moles. And then we take this moles and convert it back into grams. That's what we're going to be doing. Okay, so the first two, these types of equivalences. If you have 0.5 moles of H2O and you're converting from moles back into grams, you first have to find that molar mass, which I've done here, 18.0. I'll probably have you do 2 decimal places, I think. I have to, I'll finalize that for you guys. Alright. Notice again, when I write this, my units, moles of H2O, are across from one another. So every time that you do this, make sure that you have the same unit on the top and the bottom of your equation. And the best way to check this out is by making sure they are across from one another. Alright? So if you're converting from moles into grams, your grams is going to be on top. whatever you want, that value that you want is going to end up on top. If you're going from grams into moles, your moles is going to be on top, right? This ratio, 18.0 grams of water over 1 mole of water, can also be written the other way. These are equivalent statements, these two. But if you're trying to cancel out your moles, they're not across from each other. They're right next to each other. That's going to give you moles squared. That's not a unit. That's not a unit we care about. Okay? So you're going to be converting using these unit conversions. And your end goal is to always make sure that the unit that you start with is across from it. We have grams of sodium bicarbonate. We have grams of sodium bicarbonate. They cancel out. Alright, I'm leaving you guys to calculate how I got this 84. That's by calculating the molar mass, which we did earlier. We did all this stuff up here. Alright, it is a multi-step problem. This is a lot going on here. And I'm about to make it even more complicated. There are some practice problems here. 5 and 6, I'd rather focus on the grams to grams. It might make a good extra credit question, but you know, I really don't want to focus on how many atoms there are. I think it's a little pedantic, not as realistic as we necessarily need to be. Okay, but if we really wanted to start doing this, you'd have to start and calculate the molar masses of these two molecules. That's always the first thing you're going to have to do. Anytime I give you some kind of value, some kind of compound that I say you have this amount of it, you're going to need to know its molar mass. So that's going to be an invaluable skill, is calculating molar masses. Okay? So I will let you pause and I will come up with these answers. Okay. So here are your answers to questions 1 through 4. Oh, and I should just show you again where I have grams of glucose. Grams of glucose. I have this across moles of magnesium chloride, moles of magnesium chloride. There's a cross relationship. Cancels out the units. Okay? Notice you started with 20 grams. You had the same mass of magnesium chloride and glucose, but you have different amounts of each molecule. You have less magnesium glucose because glucose has a higher mass. It's like the elephants compared to the eggs. You have less of them even though you have an equivalent mass. Alright? So you can check your answers, see how you did with this. Question 5 and 6, it's something I really don't want to focus on. I'm going to be honest. It's something that I could throw in to make things complicated, but I think it's complicated for the sake of being complicated. I'd rather just focus on this. Okay? But here is your kind of unit conversions. Alright, so to recap what I've done so far, I have converted from moles of one substance to moles of another substance with the stoichiometric ratio. Now I have converted grams of one molecule to how many moles it has with the molar mass, and I've converted from moles of a substance to how many grams I have. So stoichiometry puts those 3 conversions into one problem. And this is where it gets really fun. Alright, so let's go back to here. This is stoichiometry. It puts everything that I've just done together. This is the type of question that you're going to get. On your quiz, especially for the honors, I will have to decide how I'm doing it for scholars. You will just get 2 questions. They're going to look like this. It's a lot of fun work to do. Right? I will give you a reaction. On the test, you'll have to balance it because that is a part of this chapter. And because I'm just very fun like that. But for now, because this is a quiz, I'm just going to give you a balanced equation. So here is ethene. Alright? Ethene right here. This is our reaction. We did this earlier. And I say, if I brought a container that had 40 grams of ethene, which is not that much, but let's just say I did. 40 grams of ethene, and I combusted it with an infinite amount of oxygen just in the air. How many grams of carbon dioxide would be produced? And if you really want to be, conscious, well, we do need to know how much carbon dioxide we are producing. because, well, one, how much are you going to get? When we start talking about dumping carbon dioxide into the air, it's important to know how much carbon dioxide we're dumping into the air in attempts to be more green. And we can straight up just calculate how much carbon dioxide we're actually dumping with this stoichiometry. So if you really want to be conscious and you say you burn a propane tank worth of gas at a barbecue, you can calculate your carbon dioxide contribution with this. Isn't that fun to think about on July 4th? Alright, so the other reason you want to care is you need to know how much product you have. If you're running a reaction and you create a drug like aspirin, you need to know how much you're making. When you create a correct dose, right? If your dose is 75 milligrams and you start out with a certain amount, if I say 75 grams of aspirin, well, you need to know how much you're going to start off with in order to get that 75 grams of milligrams of aspirin to put the correct amount in the dose. Okay? That's why this is important. We need to know amounts, put it into mass, things that we can measure out. You can't just measure how many atoms you have. That's impossible to see them. We don't have a microscope that can see, billions and billions and trillions and quadrillions of atoms. All right, so how do I solve this? What you basically are doing to get from grams of ethene, C2H4, into grams of carbon dioxide. So this is one of our reactants, and we're trying to get how much of our product we're going to get. All right, you can't just go from one to the other. There's no kind of ratio like that. We have to use this whole convoluted way around it. So how we do this? We do 3 conversions, and these mirror the 3 types of questions that I just have done. So it just puts all of that and just makes it all in one. All right, the first thing is you do, the first conversion is you convert the starting amount from grams into moles of that molecule. So whenever I say molecule 1, for the question that I have given you, I'm talking about this molecule, ethene, C2H4. Next, you convert moles of molecule 1, of this ethene, into, I'm going to color code this, moles of molecule 2. Molecule 2 is going to be our CO2. And finally, we convert moles of CO2 into grams of CO2. So essentially what we're doing here, and I will use some fun color coding here, is we are taking grams of C2H4 and we are converting this into moles of C2H4. We're then taking that amount, converting that into moles of our CO2, and then we're taking that amount and converting it into grams of CO2. That's what we're doing here. So you can see the 3 types of reactions: grams to moles, moles to another type of moles, moles to grams. And here we go. All right, let's start off with our first equation. The first thing that you always want to do every time I give you some of these questions, what do you start out with? What do I say? How much is produced, whatever, how much you started with, how much, say you get this amount. That's the number. The number that I give you is what you start with. 40 grams of C2H4. Okay? Convert this into moles of C2H4. You will need the molar mass. You should have a periodic table with you at all times when you're doing this. I'm going to come in with a lot more copies. I want you to take one home with you. You can also use online resources. ptable.com is the one that I love. It's wonderful. It's actually where I gave you that handout from. But I will give you a handout. You will need the periodic table to get these molar masses. Okay? So, my tips and tricks for this, before you start and I tell you to pause. The molar mass can be a ratio. If we started out with 40 grams of C2H4, you bet that you want the grams of C2H4 to be on the bottom. That way you have that across. You have that relationship that you can cancel out. Alright? When you're starting to do this, my second one, write the units down. I know it can be tempting just to write, oh, we're going to do 40 here times, 70 over here and 1 over here. It's a lot easier to get confused if you don't write your units down. Okay? And lastly, always start by writing down the amount that you start with. These tips are going to come up with every step of it. So I'll let you guys try this one out. This is just like those questions that I had done. The first thing you have to do is get that molar mass. So pause now, and you can have a go at this. Okay, did you get it? Let's see. Here is our first conversion. You should have gotten 1.43 moles of ethene. I also give you how you get the molar mass, and I show you there's 2 carbons, 4 hydrogens. Round to 2 decimal places. Alright, I'll be better, and I'm thinking now, I'll be more specific on it. I'm not going to take off. Unless I specify, I wouldn't take off. If I just said do it, I'm not going to take off because that's not fair. But if I say convert, calculate to 2 decimal places for every, calculation along the way, then I would start to take off. Alright. Alright, so here is your calculation. Notice here. Here is our across relationship of grams of ethene and grams of ethene. So that's how you're always going to know which one goes on the bottom, because they have to be the same as what you started with. That's our first calculation. Now, this is just like my tests, where I say, get this, use this number to get the next thing, get another number, use that for the third part. So if you guys are wonderful at my tests, then you should just be great at stoichiometry. And I'm sure you're cursing me for saying that. Okay. The second conversion, we now have moles of ethene. Now, we need to take this moles of ethene and convert it into whatever that second molecule is, which I said was CO2. I wanted to convert to CO2. So here's our balance formula. All right, this moles ratio is also a ratio. So we have 1 to 2 of moles of C2H4 and moles of CO2. That's one of the ways. Or 2 moles of CO2, 1 mole of C2H4. We have these 2 ratios. But you want the moles of the molecule that you started with, molecule 1, which is the ethene. That's this molecule that you just got, to be on the bottom. That way they can cancel out. So this is what you want. This is not what you want. You do not want that ratio. This is the ratio that you want. Alright? So, use that number that you got from the last run. If you need to rewind in the video to get it, then you can do that. Alright? Calculate how many moles of carbon dioxide you have. Okay? Here is the work. You should have gotten, just multiplying by 2 there, 2.86 moles of carbon dioxide. Now we have to finish this off strong. Okay? We got to finish this off strong by converting the moles of that second molecule into the grams of molecule 2 of that carbon dioxide. So here is my value. I'll go to green. 2.86 moles of CO2. Now we need to convert this back into grams of carbon dioxide. You're going to need to find that molar mass again. Alright? Again, because this can be your ratio, you want the moles to be on the bottom this time. Because we started with moles. So the moles should be on the bottom. That way the moles can cancel out. Alright, have a go at this. Alright, here we go. When I say have a go, it means pause. Alright, here's my calculation. I show you how I got the molar mass as well. These are the values that came from the periodic table. I think you guys should be able to do that at this point. You're going to have to do it a lot. And after all of this conversions here, after all of this math, 2.86 times 44.01, I get 125.87 grams of carbon dioxide. That's my final answer. And I'm going to tell you right now, if you just write 125.87, I will take off points. You must indicate to me that your answer, your unit of your answer is grams of carbon dioxide. You need to have that answer, or else I will take off for that. Because all of this is units, is converting units. So if you don't give me units in your final answer, after all these units, I don't want it. Well, I do. I'll give you partial credit. But it's not full credit. Okay? So, if this works for you, if doing 3 calculations, 1, 2, 3, if that works for you, fine. Perfect. I'm glad. I do want to show just a little bit of a shortcut that does these 3 conversions in just one big dimensional analysis. And yeah, I'm bringing back that word too. Okay? If this is fine with you, what I'm going to suggest, if there's anything that you're going to memorize, it's these 3 conversions, the order that you have to do them in. That's the thing I would tell you to memorize. That's the thing that I would have ingrained into, memorize this order. This is the thing that on a test you'd want to write on a note card, the order of conversions that you do this in, that you won't get for a quiz because I'm mean like that. Okay? The way that you can do this all at once is by basically just having these 3 conversion factors all at once. So I have this conversion here, this conversion here, this conversion here. Circle doesn't work that well. And this conversion here. All of that stuff, you can line those things out back to back to back and get the same answer. Alright, so here's my shortcut. Okay. The trick is to make sure that all your units cancel out as you go. You are still going to need to know those 3 ratios. The 3 ratios that you're going to be multiplying is you're going to start with, well, first you're going to start with whatever information I give you, the original amount. That first ratio, the molar mass of molecule 1, that is a ratio. Ratio number 2 is the stoichiometric ratio. This is what comes from the equation. Ratio 3 is the molar mass of molecule 2. Another ratio. Then you multiply all the top and all the bottom numbers, and then you can simplify. And you end up with the correct answer. So what the hell do I mean by this? Here is what I mean by this. I have set all of this up as one equation. Here's my starting amount, 40 grams of ethene, C2H4. Our first ratio is right here. Moles of C2H4 to grams of C2H4. This is the molar mass of ethene. And I kind of set this up. I put these lines and the titles to tell you what all these conversions are. And if you notice, here's our grams of ethene and our grams of ethene. This is how you want to set up these ratios so that you will have whatever unit is here gets canceled out. Now I'm left with moles of C2H4. That's the same thing that you did in that first calculation. Which means that when you do your second ratio, the stoichiometric ratio from the equation, so you're going to need your equation there, are moles of C2H4 and moles of C2H4. It wipes out across. And lastly, we have to go from moles of carbon dioxide into grams of carbon dioxide. So our third ratio is the molar mass of carbon dioxide. We have moles of carbon dioxide, moles of carbon dioxide, they cancel out. And if you notice, the only unit that isn't canceled out is grams of carbon dioxide, which is what I asked for in the first place. So now we've set this up. We've set up our dimensional analysis. To actually solve this thing, you take all these numbers. 40, 1, 2, 44.01. You multiply them together. 40. Well, I skipped the 1. 2. 44.1. You get this number, 3520.8. On the bottom, you get 28.06 times 1 times 1. So you end up with 3,520.8. That's an 8. Divided by 28.06. You put this in the calculator, which I did there, and what do you get? 125.47. Why is this number different? 125.47. The answer I got up here is 125.87. Rounding error. Okay? It's just rounding error. If it's that small of a difference, not a big deal. It's all, every time you cut off an answer, you get something slightly different. Not a big deal. Okay? And I also should include units. My units are grams of CO2. The last thing that I want to go over, I know this is a long video, but this is it's gonna be a long topic, is a shortcut, kind of an organization skill that I have seen, that some folks might like to use, is instead of having all of those multiplication signs, you might just want to make kind of like a checkerboard, like this. This is the same equation, but you can clearly see how across the checkerboard, in these two spots, so we're talking, here and here. This is where you should have the same units. You move over, you should have the same units. Move over again, you should have the same units. Alright, I do want to offer this as an alternative where you can put in those ratios. And you must have the same units across, from one box across to the other. This might make it just a little bit easier to visualize. So I just wanted to give you this option. Okay? So to summarize this whole long video, what you're doing is taking the mass of something and how many of those atoms you have and how many of those molecules you have as a quality. This is a quantity, not a quality, quantity, excuse me. This is a quantitative analysis. What that means is this is numbers. This is how much you have. So when we do our lab, the next lab that we do, you're going to start dealing with measuring out certain amounts of compounds, of molecules. And you're going to have to tell me, how much you end up with in terms of masses. Okay? That's what we're going to be focusing on, is this mass, this kind of, how much. A lot of the labs that we've done so far this year, besides the density lab, who think all the way back to that one, have been, they've been qualitative. They've been describing what happens and making conclusions from that. They haven't been, numbers and masses. And that's going to start to change. We're going to be introducing a lot more just math into this class. We're going to be doing these, here's a reaction. Let's see what actually happens. Okay? So, get to work on this. This is a long video, and you guys are going to really need to practice this. Alright? Not because this is difficult, but this is the type of thing that you need to practice to master. Okay?